Now we're going to go over another theme. Okay. So this theme says that if a function is continuous at b, and the limit of g of x as x approaching to a is equal to b, then the limit of this function f composed with g of x as x approaching to a is equal to f of b. In other words, that it says that when this function f is continuous at b, when this is a continuous function at b, then you can bring this limit in, providing that this outer function here is continuous at b. Okay, now let's look at this example. First of all, sine function is a continuous function. So we can bring this limit in. So that will become sine of the limit. Now, when you take this limit over here, let's see if this is a continuous function. If it's a continuous function, then we can just go ahead and do a direct substitution. Well, indeed, it is continuous because x is continuous. Sine of x is a trig function, is continuous. The sum of two continuous functions is continuous. So this is indeed a continuous function. So we can go ahead and do a direct substitution. So that will give us, inside here we get pi plus sine of pi. Sine of pi is equal to 0. So we end up with 0 at the end over here. Okay, the next example, example 2. Limit of this arc sine of this. Notice that this outer function, arc sine, is an inverse trig function. It is continuous on its domain, which is -1 to 1. Okay. So because it is continuous, so we can bring this limit in. So we can become arc sine of the limit. So when we do a direct substitution over here, we actually get 0 over 0, which is an indeterminate form over here. So we would like to rationalize this numerator, so to get rid of this square root. So we do that by multiply the conjugate of that up and down. We multiply by 1 plus square root of x up and down. That way, we're going to end up with 1 minus x in the numerator and this in the denominator. The 1 minus x here is going to cancel. That is going to give us this expression. So we're taking the limit of this function. We can do a direct substitution here because it is a quotient of continuous function. And 1 is in the domain for this function. It's not going to make the denominator equal 0. So we can go ahead and do a direct substitution here. So that will give us 1/2. Arc sine of 1/2 is equal to pi over 6. Now, some of you might forget what is arc sine. So I'm just going to go ahead and give you a quick review to refresh your memory. Arc sine of x is the same as inverse sine of x. So it's an inverse function of sine. This, whenever you see this inverse sine, inverse cosine, think about those as angle. So this is an angle in radian, which is in -2 to √2, including this 2n, such that sine of that will be equal to whatever inside here, which is x. For example, we know sine of √3 is equal to what? Sine of √3 is equal to √3 over 2. Therefore, inverse sine of √3 over 2 is equal to √3. √3 is in this -2 to √2, right? Okay. So √3 is an angle in this such that sine of that is equal to this number in here. Another example, sine of √4 is equal to √2 over 2. Inverse sine of √2 over 2 will be equal to √4. So pi over 4 is the angle in -2 to √2 such that sine of that equal to √2 over 2. Okay, sine of √2 is equal to 1. So inverse sine of 1 will be equal to √2. Okay. this theme says that if the function g is continued at a, and the function f is continued at g of a, so when you compose them, compose f with g, then this composition of this function is going to continue at a. So if we want to say this in one sentence, you can try to remember this way. So a continual function of a continual function is again a continual function. Or you can say the composition of continual functions is again continuous on its domain. Okay. So let's look at this example. Where are the following functions continuous? I use this notation for functions. This function over here, let's rewrite that as the composition of two functions. So the outer function is going to be the sine function, sine x. The inner function is the x squared function. The outer function is continuous on its domain, which is all real number. Inner function here is continuous on all real number. It is a polynomial function, so it is continuous on all real number. So when you compose these two continual functions, you're going to get a continual function again, because the theme says that the composition of continual function is again continuous, right? H being the composition of f and g, again, it's going to continue on its domain, and the domain for that is going to be all real number. Second example, let's rewrite this using the outer function f and the inner function g. The outer function will be the Ln function. So Ln of x is outer. The inner function here, it is 1 plus cosine x. The outer function is continuous on 0 to infinity. The inner function is continuous on all real number. The composition of continual functions is again continuous. So this big F function is continuous on its domain. Now we just need to find its domain. To find the domain, look at this one here involve Ln. So the whole quantity that you take Ln with has to be strictly greater than 0. So we need this 1 plus cosine x greater than 0, which means cosine x is greater than -1. Now cosine x, the graph look like this. Okay, it's always -1 or above. So when it's greater than -1, let's think about when does cosine x equal -1. Looks like cosine x equal -1 here, here, and here. When x equal to plus or minus pi, plus or minus 3 pi, etc. So in order for cosine x to be greater than -1, x cannot be equal to plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. So the function big F is continuous on its domain, which is all real number x, such that x is not an odd multiple of pi. So I use 2n plus 1 here, where n are integers. Then this 2n plus 1 will represent an odd number. So x does not equal to any odd multiple of pi. So that's the domain for that function.